This is the last lecture on structures. This lecture is completely dedicated to the concepts of fatigue. Halfway the 1950s, the Dutch aircraft manufacturer Fokker presented its new aircraft, the Fokker F-27 Friendship. This aircraft can be seen on this picture. This Fokker Friendship had a number of new features like metal bonded structures, already some composite parts, and a pressure cabin. Such a pressure cabin was needed to fly at high altitudes above 3,000 meters. Above this height, the air becomes too thin to breathe easily. Most new aircraft in those days had a pressure cabin. Using a pressure cabin enabled the aircraft to fly at higher altitudes where the air density was low. Combined with the new jet engines introduced just after the Second World War, fast and long-distance air travel became possible. This gave a tremendous boost to air travel. The pressure cabin also introduced new forces in the skin of the aircraft. In the previous lecture we have learned that the metal skin was load-carrying. When a pressure cabin was introduced, the skin was loaded even more. On this slide, the circumferential stress or hoop stress is calculated. We assume that the half cylinder is 1 meter in length. It has a thickness of T and a radius R. The pressure in the cylinder is P2 and the pressure outside is P1. So the pressure difference, delta P, is P2 minus P1. When we need equilibrium, the downward forces should equal the upward forces. In this case, 2 times the hoop stress times the sheet thickness equals the integral of delta P over half the cylinder. After some manipulations, we can obtain a very simple formula. Hoop or circumferential stress is equal to the pressure difference times the radius of the cylinder divided by the thickness of the skin. The pressure works evenly in all directions, so there is also a longitudinal force or stress working in the fuselage skin. This stress can be easily calculated using the following sketch. When a simple disc is used as the end cap or bulkhead of the cylinder, the calculation is simple. The pressure force to the right is equal to the pressure difference times the area of the disc. The opposing force is carried by the skin. In this case, a stress times the circumference of the fuselage times the thickness of the skin. Manipulation of the formulas results in a longitudinal stress in the skin, which is half the size of the circumferential or hoop stress. To get an idea of the magnitude of these stresses, I will give the following example. Assume we fly in a small aircraft, about 50 to 100 passengers, having a fuselage diameter of 4 meters, so the radius is 2 meters. We fly at 11,000 meters, which is a normal altitude. The outside pressure can be calculated by the formulas of the International Standard Atmosphere. This outside pressure is just over 22 kilopascals. The pressure inside the cabin is maintained at nearly 71 kilopascals, which is 70% of the sea level value. With these values, we can calculate the pressure difference. Next, using the radius and pressure difference, we can calculate the value for stress times thickness, which is over 96,000 Newton per meter for the hoop stress and half that value for the stress in longitudinal direction. Depending on the skin thickness, we obtain different hoop and longitudinal stresses. 2 examples for the hoop stress are given. The hoop stress is almost 100 Newton per square millimeter for a skin thickness of 1 millimeter, or nearly 50 Newton per square millimeter for a skin thickness of 2 millimeters. Note that the maximum allowable stresses for metal skins are close to 100 Newton per square millimeter, and that these stresses result from the pressurization load only. In reality, we may have other loads as well, like bending and torsion moments. The calculations done so far has been for undisturbed cylinders. In reality, we do have a lot of cutouts in cylindrical fuselages. cutouts like windows, doors, hatches, etc. Every cutout creates concentrations, stress concentrations, and increases the local stresses. In order to stay below the maximum allowable stresses, the skin has to be reinforced locally. The skin thickness has to be increased. Pressure cabins are also related to metal fatigue. As said before, after World War II, new aircraft were developed made of aluminium, equipped with jet engines and a pressure cabin to enable them to fly at higher altitudes. The British de Havilland Comet was the first operational jet aircraft of the new age. Two of these aircraft fell from the sky in the early 1950s, and nobody could tell why. After grounding the aircraft and thorough investigation, metal fatigue in rectangular shapes was proven to be the cause of these accidents. Up to that moment, metal fatigue was underestimated. Due to some unfortunate design choices, the comets fatigued and failed during flight. What is metal fatigue? To make it simple, almost everyone has broken the paperclip. If not, you should try. Just by bending back and forth multiple times, the paperclip fails. If you would like to break the paperclip simply by force, this would be impossible. So fatigue can be characterized by repetitive loading, in our case of the paperclip. Another feature is that the applied load is much smaller than the static load we need for failure. This may also happen in aircraft, where the fuselage is pressurized every flight. Often other fatigue loads are on the wings, where the aircraft flies in a turbulent atmosphere. In this graph, we see a so-called SN curve of an aluminium alloy. The horizontal axis shows the number of cycles logarithmically. The vertical axis shows the failure stress. At cycle 1, just a static test, the material fails at a stress of 320 megapascals. At 100 cycles, the failure stress is 260 megapascals. At 1000 cycles, the failure stress is 200 megapascals, and at 10,000 cycles it is 160 megapascals, etc. Further increase in number of cycles results in lower failure stresses. This is the same as we experience with the paperclip experiment. So more repetitive loads reduce the maximum applicable load. Fatigue in metals is often visible by cracks in the sheets. Usually such crack starts at a notch or another stress concentration. For example, at a rivet hole. It takes time to start or initiate a crack. The time required for this is called crack initiation period. Once a crack is present, the crack grows, and we talk about crack growth period. These periods are presented in this figure. Along the horizontal axis we write the number of cycles. Along the vertical axis we plot the length of the crack. As can be seen, it takes time to initiate the crack, the initiation period. Once started, the crack will be invisible for some time because it is very small. Of course, special equipment can be used to detect cracks in an early stage. Once the crack is visible, it will grow faster and faster. The crack length follows an exponential curve. If you don't stop or repair the crack will become critical and the component or structure fails. However, to prevent failure, we need to inspect the component frequently. Once a crack has been discovered, we need to repair the component. In the ideal case, a cracked component is inspected several times before the crack can become critical. Of course, it will be too time-consuming to inspect all locations of stress concentrations on a regular basis. Therefore, only specific locations of aircraft are inspected. Those locations are identified based on the type of loads, the design of the components, and the applied materials. Typical loads which may induce fatigue are wing loads, like remove and maneuvers, forces introduced by flaps or engines. And for the fuselage, the pressurization cycle is very important, as well as the loads transferred by the wings and the tail section. In this last section, we looked at fatigue of metallic structures. This has been and still is an important phenomenon in the design of aircraft. As we have seen, it is the repetitive nature of the loads that characterizes this type of damage.